Hello everyone, can you hear me clearly? Good morning to all of you. Let me know if you can hear me clearly. Okay, hello Anuj. So Anuj is confirming from YouTube, and I see Arshad is confirming from Facebook that they can hear me. Okay, that's great. So this is an open session on Math Olympiad geometry, and we were discussing geometric transformations. So if you have attended the last few sessions for class 7 and 8, you will remember that we are discussing certain things called geometric transformations. So what are geometric transformations? They are different ways of transforming a particular figure in the plane, and they are used to solve geometry problems in a little different way than normal geometry solutions. So in a normal geometry problem in school or elsewhere, the way we do it is we have a set of theorems, and we use that set of theorems to solve a problem. Maybe we do some angle chasing, maybe we put some theorems at work that has been proved before, and so on. Okay. But in this style of geometry, we do not really do angle chasing in that way. We instead look everything in a dynamic manner. We see in our imagination, we see everything moving. We see everything moving. Okay. And that is kind of interesting because that helps to solve certain type of problems very easily. So let me go ahead and briefly review what we have already done. This is something that we have already done in class. So if you should be able to remember or recall this particular thing. So let me put this slideshow like this. Okay. So I'll briefly recap that we were working on this particular problem where our goal was to show that two lines are equal. So this was the central problem that we were trying. Remember that in any of our classes, we usually go from problem to concept. That's really the style you should follow as well. You should start with a problem and then slowly learn the concepts that are required to solve the problem, right? Okay, so what was the problem? Suppose ABC is a triangle. We started with this. Suppose ABC is a triangle. Draw equilateral triangles DAC on the side AC and EAB on the side AB. So we have two sides of the triangle, AC and AB. We draw two equilateral triangles on two sides of it. Okay, that's great. Remember, the triangle ABC need not be equilateral. The triangle ABC itself doesn't need to be equilateral. The triangle ABC itself could be anything. The triangle ABC could be a scalene triangle, could be an isosceles triangle, that's fine. What we just did is we took two sides of the triangle ABC, AB and AC, and we constructed two equilateral triangles on two sides of it. Okay. So this is something we have already talked about, so you should remember this. Now the next thing is what we do is we want to show that CE is equal to DB. So we join CE, the point C, with the vertex opposite to it E, and we join BD, so with the point B with the vertex opposite to it D. So it's a very simple idea. So we join CE and BD. We want to show that no matter what triangle ABC you start off with, these two segments will always be equal. Okay, so how do we go about that? For that, we need to understand something called rotation. We already talked about it. We already talked about rotation. Let me explain that very quickly one more time so that you remember it. It's a type of motion on the plane. Rotation is nothing but a type of motion on the plane. You fix a point O, which is the center. So maybe this is O, the center. By the way, I'm not sure if you can see my cursor. Can you see my cursor? I think you can. Okay. So this is a pointing tool. All right. So this is O, the center, which is a fixed point. Remember, rotation is a type of motion on the plane. So it will move around points on the plane. It will move around points on the plane, except for this point O, which is the center point, which we call the center. It's the only fixed point of this particular motion. All right, that's very good. Then what we do, we choose another point P. This is the point P, another point P on the plane. And this will be a moving point. This will be a moving point. And the way we do it is we join OP, and we try to move OP. So we will push OP, fixing O. We fix O, we pin down O, and we push OP. All right, so that's great. So if we do that, what the type of motion that we will encounter is what we call rotation. So if we push OP fixing O, suppose it goes to a point OQ. So P goes to Q. If you do that, suppose you fix O and you push OP, then it moves on the plane and P goes to the point Q. So if that happens, then the motion that has happened, we call it the rotation. So the real question that we asked in the last class is how to measure this rotation. Kaustubh is asking, is this every day? So this is an open session, Kaustubh, for during the lockdown period. We are trying to reach out kids from different parts of rural India and urban India. But you can go to cheenta.com for other classes. Okay, let's continue with this. So how much rotation has happened? That's the real question. Remember, we have to think of ourselves as cave people. We do not know what are angles. We do not know anything else. We just want to know that if we fix O and if we push OP, it has reached OQ, how much rotation has happened. We want to measure it. We want to know how much rotation has happened. Okay, so the key idea for doing that is to use something called arc over radius. We discussed it already. We will discuss it one more time quickly. So suppose again we have OP. P is the initial point. O is the center point. P is the initial point. O is the center point. Now P is traveling. When you push OP like this is O, suppose. When you push OP like this, the point P, suppose that's here, it is traveling along an arc. So I'll show it to you in a moment. So this is the arc. This is the arc in red. If you look at the path that P has taken to travel on the plane, it will travel along this red path, which we are calling the arc. If you ask me what is an arc, arc is precisely this path, this red path along which the point P has traveled. Okay. So if you look at this little animation I just did, so I'll do it one more time. This little animation will tell you how the point P has traveled along that path and reached the point Q. So the point P traveled along that path and it hits the point Q. Correct? Okay. So now our question is how much rotation has taken place. So one thing you can do is you can measure the length of the arc PQ. You can measure the length of the arc PQ and you can say, okay, maybe that is how much it has traveled. Maybe it has traveled along, the quantity of rotation is probably the length of that arc. But we will be in trouble if we do that. So you have to be very careful about it. So let's see why. If you take another point, let's say another point is M. If you take another point M on OP, then if you do the same rotation, it will reach the point N. The point M reaches the point N, but this time, this is how it goes through the arc. So this Mn is the new arc. So now the question is, if the length of the arc is the quantity of rotation, then the same rotation will have two different values, one for PQ arc length, one for MN arc length. In fact, if you take any other point in between, they will give you different arc lengths. So just telling the length of the arc is not sufficient. So what do? Well, we have another way. We take the arc over the distance from origin. So our key observation, and this is really the turning point of geometry in some sense, our key observation is this, that if P gets closer to O, if P gets closer to O, the center point, the length of the arc also reduces in size. As P gets closer to O, the length of the arc also reduces in size, so the ratio of arc and radius remains constant. So arc length gets smaller as P goes closer to O, but the ratio of arc over radius remains constant. So instead of taking the length of the arc as the measurement of rotation, what we do is we take the length of the arc and we divide it by the length of the radius. And then we take that ratio as the measurement of rotation. So this is the, okay. So I want to show you by experiment how this actually happened. So you can actually see this happening in if I use something. Okay, let me just see. So let's do one thing. Okay. So in the meantime, I would ask you to actually go ahead and draw this picture in your notebook. Mark a point O, take a length, let's say OP. Suppose OP could be 5 centimeters or something. Okay, let me just add something to the screen. Let's see. So here we go. We have a better picture. So this is a geometry software. I highly encourage all of you to actually look into this. Okay. All right. So can all of you see the little geometry doodle, the software that I'm using here? So this is a very nice software. It's known as Geogebra. Okay. It's a very nice software. So we will be doing the experiment that ancient Greeks and Indians did with this sort of thing. Okay. So what did they do? They first fixed a point. Let's fix a point, which is our center point. Let's call that point A. Okay. So rename it as O, sorry. Let's call it O. And let's take another point P. Let's take another point P. Let's suppose P is 3. P is 3. Let me rename that as well. Let's call it 3. So this was the ancient experiment that Arjabhatto actually did. So let's join the segment. Let's join the segment OP. Let's join the segment OP. Let's not show levels, and let's change the level into new points. So can all of you see the, okay, so I think all of you can see it. All right, you should do this experiment in your home as well, in your notebook as well. So all of you can see OP, all of you can see OP. So what I'll do is I'll just turn OP about the point O. I want to turn OP about the point O by a certain amount. So I want to make a rotation. So let's do that. Let's try to rotate. So my object is F by, let's say, 0.5, something like this. Great. So you see, we get P prime. That's great. We got the point P prime after my rotation. So let me do one thing. Let's animate this stuff. It's kind of, it will be fun. So I'll just do some fun animation here. just to make sure that we all understand what's going on. Let's take the point t and range it from 0 to 3. Let's do it like this. Okay. Let's throw away p prime. So we are just doing an experiment. This is the same experiment that Aryabhatta or the ancient people did, just without the software. They just did it with a string and a ruler. So it was excellent. Okay, so what I'll do is I'll now again rotate this f, but only by this t. So now let's see. So I will hide this one. Let me hide this one. And let me do one thing. Let me hide this one as well. Okay, cool. And okay, so can all of you see this rotation happening? Can all of you see this rotation happening? This OP is sort of moving. Okay, so this is beautiful. Can I make the screen bigger? Okay, maybe like this. I don't know. I don't think it helps. Sort of doesn't. Okay. So remember, this is the experiment that people did thousands of years ago, and that sort of created. So what is our experiment? Let's see. So we will do one thing. Let me just remove the axis and the grid just to make this picture a little bit nicer. It should look a little bit nicer. Okay. So this is fine now. All right, great. So what is our experiment? Our experiment is to take the arc. So let's take the arc. So I'll take the arc tool from here. Just to, yes, here is the circular arc tool. So this is the center, this is the point, this is the, okay. So this PP prime is the arc. PP prime, this particular length is the arc. This is the arc, this thing. This is the arc, and the length of the arc C is given here, 2.48. Can all of you see the length of the arc? It's just right here. So if I put my cursor on the arc, it shows that it's the arc C, and the length of the arc C is 2.48. The length of the arc C is 2.48. So let me do one thing. Let me just put this text here. So arc is 2.48. This is arc PP prime. Good. All right. So can anyone tell me what is the distance of P from the center O? What is the distance of P from the center O? What is the distance of P from the center O? Can anyone tell me what is the, I started with a distance of P from the center O. Maybe if I open the grid, you will see it again. So maybe I will put the axis as well. Okay. So you should be able to remember, you should be able to read it off. What was the distance of P from the center O? What was the distance of P from the center O? Give it a try, all of you. Okay, Shikha Mahato is saying, okay, it's 3. Excellent, excellent. Very good. Very good. It is indeed 3. So let me just put this here. So Arshad Jamal is also saying it's 3. That's very good. So the arc is 2.48. The radius is 3. So let's do this. Let's come back to this. So the radius is 3. So can anyone tell me what is the ratio of this arc over radius? What is the ratio of this arc over radius? You can just divide 2.48 by 3 and give me the final value. Divide 2.48 by 3 and give me the final value. What is the ratio of arc over radius? So, okay, hello Lakshi. So what is the value of arc over radius? What is the value of arc over radius? And you can use your calculator or something, it doesn't matter really. Can you compute the value of arc divided by radius to give me the ratio? Okay, 0.82666. Excellent, very good. So uh, let me write that. 0.82666. Very good. Now we will continue with our experiment. So what I'll do is I will open up the axis just for the sake of this. So what I'll do is I will put the point at, instead of P, I'll put it at 1. Instead of 3, I'll put it at 1.5. Okay. So I'll just rename it as M. Okay. And then I will rotate M by T. So I'll get the point M prime here. So now let's find the arc M prime. Let's find the arc M prime. So let's take O M prime. Great. So what is the length of the arc now? Can anyone read it off from the, can anyone read it off from this particular picture, whatever is in the left hand panel? You should be able to read off the length of the arc prime from the picture. So I can just use a different color, maybe that will be sort of interesting. So let's use red, and maybe I can change the style to thickness to 7 maybe. Okay, good. So prime. So can anyone read off prime? Okay, excellent. As Arshad is reading it off, it's excellent. It's 1.24. So this new arc is 1.24. Arc prime is 1.24. Okay. So do anyone remember the length of the radius? That is the length of OM. Do you remember the length of OM? Length of OM. So let's see if anyone remembers the length of OM. Aha, the length of OM was 1.5. If you remember this, the length of OM was 1.5. So the radius is 1.5. The radius is 1.5, right? Great. So what is the value of arc over radius now? So the value of arc over radius is equal to, we have 1.24, sorry, this is 1.24 by 1.5 is equal to, if you divide 1.24 by 1.5, what do you get? Sorry, yes, you get the exactly same thing. You get the exact same thing, isn't it? You get the exact same value. It's 0.28266, something like that. So approximately 0.3, 0.83, 0.8266. Right? So exactly the same value, that's what you get. So this is the point, friends. You should remember that we are doing this using a software. The software can actually measure the length of the arc. It's able to measure the length of the radius. But in the beginning of times when there was no computer, what they were doing is they were literally taking a fixed point and they were taking a length OP, and then they were turning it. And then they were observing that though the arc length is reducing, so from 2.48, it became 1.24, right? The arc length is reducing. The same thing is happening with the radius. The radius is reducing as well. But the rate at which they are reducing, they're completely different. They're completely same, exactly the same, sorry, exactly the same. That's why the arc over radius thing remains exactly the constant for a given amount of rotation. So for this rotation, what is the value of this rotation? Let me ask you. So if I put this, etc. So how much rotation has happened? If I ask you this, so how much rotation has happened? If I ask you how much rotation has happened, how would you answer this question? Exactly. So if I ask you how much rotation has happened, the default answer should be 0.8266. Do you see why? It makes sense. It makes so much sense. Because no matter where you take the starting point and you take the end point, this arc length and divided by the radius length remains exactly the same, and it's 0.8266. And if I tell you this ratio, you can directly replicate the rotation. You can exactly find out the rotation. So that's why we say that 0.8266 amount of rotation has happened. Okay. Now, if I go back to this particular screen, okay. So let me just show this to you. Look at our problem. We wanted to show CE is equal to DB. That was our problem. There was this ABC triangle, and we erected two equilateral triangles on two sides of it. We wanted to show that CE is equal to AB. CE is equal to AB. How do we show it? How do we show that CE is equal to AB? So what we do, and this is the most interesting part, we perform something called rotation. We perform rotation. So this is the clever part. So let me just quickly tell you how to do this so that we all understand. Oops, sorry. Let me just share the correct board now. Okay. So let me draw the picture here. If you have ABC as a triangle, oops, sorry, can you see it? Maybe it's there, maybe it's not. Okay, maybe it's not. So we have the triangle ABC here. So we have A, B, and C. And we draw two equilateral triangles on two sides of it. So I'll change the color. One of them is like this, and the other one was like this. So we draw two equilateral triangles on two sides of it. This one was E, this one was D. And we wanted to show that CE is equal to BD. This was our goal, right? So what we will do is we will perform a rotation. So we will do a rotation that will take CE exactly on BD. That will take CE exactly on BD. Okay. So how do we do it? How do we perform the rotation? Okay. So for the first step that is needed to perform a rotation is to actually find the center of rotation, which is the fixed point. So first step, find the fixed point. So this is actually true for any substantially hard mathematics problem. For any substantially hard mathematics problem, if you really want to solve the problem, one of the things that you need to do is to find out the fixed point of any transformation. So I talked to you about this a few in a different seminar, that in any transformation, when everything changes, if something does not change, that is the most important thing. That is the clue into understanding the system. If in a system a lot of things change, and if something does not change, that thing that does not change is the key, sort of the key to the system, key to understanding the system. One of the most famous example of this is the velocity of light in vacuum. It doesn't change. Even when the world changes a lot, it does not change. So in this particular system, since we are studying rotation, what is it that is not changing? The fixed point, or the center of rotation. So I'll tell you the center of rotation. The center of rotation is the point A. How do I know this? Well, a little bit of thought would tell you that if you want to really shift EC on BD, then both the position of all of these 4 points must change. All the 4 points B, C, D, E must change their positions. Otherwise, BD will not fall on CE. BD will not fall on CE. So they are all moving. There cannot be the fixed point. Of course, some other point on the plane could be the fixed point. But apart from these 4 points, the one point that we have already drawn is A. So it makes sense to try with A. And it happens so that it works with A, which is a fantastic thing. So now what you have to do is, you have to use a little bit of imagination. You have to think that you are rotating about A, and CE is exactly falling on BD. You are rotating about A and CE is exactly falling on BD. How can you think about it? How do you imagine this? Well, you do this. You think about this side folding into this one. AE sort of folding into AB, and AC folding into AD. So AE folding into AB and AC folding into AD. It is very important to imagine this in your mind. It's not important to really reach the final solution. I mean, the final solution is probably the most uninteresting part of a problem. The problem itself has many interesting things going on. So AE folds to AB and AC folds to AD. Okay, so in your mind this should happen. So this one is sort of turning like this. This is AE, suppose, and this is AC, sorry. So this is AB, AE, and this is AC, and it's turning like this. AE is falling on AB, AC is falling on AD. Okay. Thanks, Shivam. All right. So now that we have this is a very non-rigorous way of saying this. Of course, it's not very. I've not told you exactly what angle of rotation we have used, how much rotation has happened. So this is up to you. This is a very simple thing. You can just think about it like this. How much is this angle? What is this angle? After all, this is an equilateral triangle. This is an equilateral triangle. So you know this angle, you know the value of this green angle, and you also know the value of this. So this black thing is also an equilateral triangle, so this red angle is also known to you, and both of these angles are 60 degree, as Arshad or Prabhat Kumar Chattopadhyay is saying. Both of these angles are 60 degrees, and since both of these angles are 60 degrees, your rotation must be through 60 degree. It's a 60 degree rotation about the point A. It's a 60 degree rotation about the point A. Now the next question is, why will E exactly fall on B? Why will E exactly fall on B? I mean, it could have fallen here. Maybe it falls a little bit closer to A. Maybe it could have fallen here. Maybe here it is the destination of E. Why is it exactly falling on B? Well, it is exactly falling on B because AEB is an equilateral triangle and the length of AE is equal to the length of AB. That's the beauty of equilateral triangles. Length of sides are equal. So not only AE will fall along AB, AE will fall exactly on AB because the length of AE is equal to the length of AB and the angle is 60 degree. The same logic holds for C falling on D. AC will exactly fall on AD because the length of AC is equal to the length of AD because this triangle is equilateral. There you go. E falls on B and C falls on D. Since E falls on B and C falls on D, therefore CE will exactly fall on BD. Now if you rotate something, its size does not change. So CE must be equal to BD. That's it. We are done. So anyway, I hope you enjoyed the session. We will meet again next week and continue the discussion. Till then, stay safe and stay at home. Bye.